Okay, start again. So tonight we're going into both CLT and green roofs. I'll try to split those up into two separate videos because in the search task they're treated as two separate sections of the report. So article, it's about over a year old now. Article about building docklands using CLT. Also, I've got a couple links to CLT manufacturers in Australia. So their factories have only just opened and just started.
Oh, right.
So the thing about CLT is that previously it wasn't manufactured in Australia.
Right.
When was it? 2007. It started getting used in Europe, and then started getting used a little bit in Australia, but all the panels had to be imported because of the engineering around it. We didn't have the right timber in Australia, or the engineering hadn't been
developed for our timbers.
Exactly, developed for our timbers. Whereas that has happened now. And so now we've got a factory in Melbourne and one in WA.
Right. So now CLT, the structure of CLT, what is it?
Yeah. So let's have a look at that. So I've got those two links, and we'll have a look at those two links later on. And then also this one's a video about a CLT building that you can go in. Or the owner takes you inside the building there. So apologies about the pixelation. So this is a building in Kent Town, on King William Street, Kent Town, using cross-laminated timber. And basically what cross-laminated timber is, it's like large, thick panels made up of like a glulam beam. So it's solid pieces of timber glued together in what's called lamellas, and then you come up so it's also known as tilt-up timber or jumbo plywood.
And
both of those are fairly apt descriptions.
Right, and this is very similar to massive timber.
Yes. So another description of massive timber.
So massive timber is actually a description for CLT.
Yes, yeah. Because what it is that you're essentially dealing with is large sections of just solid sections of timber.
Right.
So very, very similar to precast or tilt-up concrete panels in their shape and formation and fixings as well,
right.
except that it's timber. So it's made entirely of timber. Of course, it has the properties of timber, being a thoroughly natural material and a material that sequesters carbon. So trees take carbon out of the atmosphere and put it into cellulose fibres, cut trees down and turn them into timber products. Because of that, it has a particularly low embodied energy, as you know. So many of these things are the same as your considerations for your timber framing early on. It provides continuous insulation to a building. So when you've got a timber framed building or steel framed building, you have points at which you've got you've got different insulative values of your frame and the insulated portion between your frame. Whereas with the CLT, it's continuous throughout.
Yeah.
It also produces very well sealed buildings. So it's like your structurally insulated panels in that fashion. So manufactured in a factory with CNC machining, incredibly accurate. So very little tolerance for error on site, but very, very accurate. It goes together very well, and you get a very well sealed building. Also, being timber, so same properties as timber used in other situations. It chars, but will maintain its stability while it's charring. So for the uncharred portion, the piece of timber is as strong as the uncharred portion. Being a solid timber piece, it's much harder to burn that than it is to burn smaller sticks of timber, as you can imagine. But it's still a combustible product, so it can't be used in non-combustible, in situations where you're required to have a non-combustible element. So to meet fire resistance levels for fire separation walls, or for areas where you need something to be non-combustible, say such as bushfire requirements, then you need to clad it with a non-combustible product. So for your fire separation walls, you clad it with your fire resistant plaster board.
Yeah.
So the same as your details with any other product that you might want to use for fire separation walls, the manufacturers produce those details
Well, I'm
for
actually
meeting
thinking
those
that would
FRLs.
be exceptionally poor in terms. The only thing you'd have a problem with would be exceptionally poor in terms of like sound. It would actually probably really be quite solid in terms of transmission of sound.
Well, it's there is that information on the manufacturers'
Websites.
Yeah, websites as well. And the way that you meet your sound reduction levels is once again with insulation and plasterboard details. But we can see on I'll just skip ahead a few. So a fairly simple detail here where we've got our CLT in the middle, battened out, and insulation gives you the sound resistance rating of 62, which
fantastic.
Yes, which is fantastic. So it's better in terms of your sound reduction than just your standard timber framing. So it performs better in that regard. That'll be the thing, I guess. Compare it thickness for thickness with concrete.
Well, concrete's got very poor sound insulation, is what I worked out, which is actually my experience. But I know that people kind of take it to be somehow or another it's a great sound insulation, but it's actually not. It's really bad sound insulation.
Yeah. Where it performs well is in impact, that sound. From impact in comparison to lighter framing, which tends to vibrate more and act like a drum.
Yeah, if you've ever worked in the middle of a multi-stories construction, oh my God, the flaking sound, I had no idea what the expression for it was, but the flaking sound is horrific. You may as well be right next to the hammer drill in the basin.
Yeah.
I mean, so there is that. It doesn't, and in fact, I've heard people's shoes clattering on concrete floors above me. And then I found some research that was done in Newcastle, where it was found that actually you're getting a lot of from above. You get a lot of noise. So,
because of the reflectance of the material and
that's really great.
So actually, well, I guess essentially it's very easy to say it's a less reflective material than your concrete because it's not as dense as the concrete. So now, as I mentioned before, so previously you couldn't buy CLT panels manufactured in Australia. They're manufactured from spruce in Europe and brought here, whereas now there are radiata pine engineered panels. So it's created by your standard size. Well, they use actually I don't know exactly what size timber they use. Fairly standard size. Let's say to keep the conversation short, 70 by 35s. Although I think they're larger than that. You've got 70 by 35s that go through a machine, get planed. Defects get cut out. They get joined together. So the defects and finger jointing all happens within a machine that detects dead rot, dead knots, etc., and passes through, and it's a machine-controlled process. Those, when they're joined together in layers called lamellas, and they're glued together with grains alternating in the other direction. Hence that term jumbo plywood.
Right.
So we've got grain grains running in alternate directions. Panels are then pressed together, sanded, and then cut by a CNC machine. So, got a link to a video. It's quite a loud video. Drop that down there.
They actually have to use the same grade of timber, wouldn't they, to actually get the same effect. They wouldn't have to use the same grade of timber to get the final effect because of the engineering process.
They would have. I'm not sure how they stress grade their timber, but they would want their stress grading to be fairly uniform.
I mean, yeah, fairly uniform, but at the same time.
So so that machine we saw just before was the finger jointing machine. So it cuts them, creates the finger joints, and joins them together. And then just a whole series of robots to stack them into place. G'day. Grab a seat. So what we're looking at now is a video on how cross-laminated timber is produced. So cross-laminated timber, it's basically large panels, timber made up from small pieces of timber. They're all planed and cut and arranged in a fashion that they'll be able to produce these large panels, much like tin-cut concrete or precast concrete, except it's with timber.
Yeah.
So,
It's the thing about Hebel that gets me is that to get stuff that is actually structured is incredibly expensive. So, I mean, I'm looking at this and it's not going to be cheap. But it is, if it produces those kind of those kind of acoustic
yes,
you've actually now got an alternative to Hebel, which is completely structural.
Yes, yeah. And that's it. You do get a structure within a very thin,
70 metres is thin.
Yes, thin material. So we can have a look at span tables later on as well, but you do get very impressive spans per thickness from this material.
And also vertical spans.
Yeah. And very good air tightness for your buildings as well. Yeah, and sequester carbon in the process and natural materials. Okay, so PVC glue, that's not a natural material, but a high percentage of natural materials.
Pardon?
But a high percentage of natural materials.
Very, very high percentage of natural materials.
that's it. All these stacked together and then pressed down to glue together.
But because of the cross-lamination, you could probably produce a far higher strength with far lower grade timber.
Yeah,
The cost offset.
yeah. So it's like engineered, like any engineered timber in that in that manner that you.
Yeah, actually stuff.
So that's the panels. So they're manufactured into large panels, and obviously with your design, you engage the manufacturer fairly early on in the process, and then start designing your building around their manufacturing capabilities. Post design, well actually no, sort of partway through design, another thing you have to think about is delivery. So yes, you may be able to manufacture panels to a certain size to meet the design that you wish, but you still need to get them into place. So it's exactly the same sort of considerations you have with precast concrete panels. So your panel width and length, the ability to get the truck in there where it needs to be. You might be able to transport it on the road, but can you get it down those narrow laneways and things like that? In places like Melbourne or in inner city areas in Adelaide, where it will be placed on site if it's not going in straight away, where you put a crane, etc. And you want to have it covered as well. You don't want it to be out in the weather, and also you want to sequence your building process to ensure that it's not exposed to weather for long periods. And also that information you're going to get from your manufacturer about how long that can be in the weather as well. But then, particularly like tilt-up concrete construction, you've got to think about your sequence of installation as well, and you have to specify that with the manufacturer that you want these particular panels on the top and these particular panels on the bottom, so you can be craning off. So yeah, as you go. Or if you know that you're not craning straight off the truck, then you might want to have it ordered exactly the other way, so the panels that go up first are actually located on the bottom. So it's about organisation. Yeah, it's about that organisation. So for small panels, you can carry them in by hand, but for the bulk of your panels for CLT, you're going to have to crane them into place because they're fairly heavy. Obviously, you have to think about that delivery and placement, overhead structures and cables. So obviously, a common issue in inner city areas, and that you're going to have to note on your site visit how you crane things into place, and also wind. Can't always allow for wind, but it has to be considered. Fixings for your CLT are really quite simple. The majority of your fixings are with really large screws, so it's very similar to your structurally insulated panels in that manner. Is you use timber screws for fixing, and there are plenty of fixing details on the website, so I'll show you a little bit later. In regards to building compliance, you will not find any reference to it in the NCC, in either Volume 1 or Volume 2, and you will not find an Australian standard relates to CLT. There is not a deemed to satisfy approach for CLT. It's an engineered system that meets performance requirements.
But the manufacturer will be the guys that certify it.
Yes.
Which means that actually you don't need as much engineering as you need to worry about, because you don't have to go to an engineer to do the service. You go to and buy the product, which includes the engineering.
Yes, good distinction. So you may employ a structural engineer in the design process, or the more likely scenario is that you will engage the manufacturer early in your design process and say, this is what we're looking to do, what are our capabilities around this, and they will engineer that system for you and tick the and let you know about the manufacturing capabilities at the same time to do that. So so they have all of that engineering, but there is still information. There's still that product information on your websites to get some initial idea of what is actually going to be capable, what you can do with it, which is what you want to do before you start engaging a manufacturer to get involved in the project. So to meet your FRLs, it requires protection. So various different protection details on your websites. Whether got two different details there to meet 90 fire resistance.
10 mil plasterboard to me was that it's still got 90. The only difference is the what's the name of the second one? Is the sound insulation the second one?
Yeah, the difference between these two systems is this system has the fire resistant plasterboard adjacent the CLT, then battened out, and then your standard plasterboard on the outside. You might want to use a detail like this if you couldn't use fire resistant plasterboard on the other side because you needed impact resistance or something like that for a disabled unit or so. You can now buy fire resistant, moisture resistant plasterboard, so that that aspect is taken care of. But where you want to use a different type of plasterboard, then you may use this particular system. But it ends up having a thicker wall with a lower sound resistance, or you can batten out straight off your CLT with your insulation and then 2 layers of fire resistant plasterboard either side. To meet.
Yeah, so that's a 70 mil. So on top of your 70, so the total width of your wall is 70 mil studs, 7 mil of is it that's more like 7? So
70 mil CLT, 2 lots of 60 mil insulation. So you're at 190 plus 2 layers of 13 mil.
So about 200.
Yeah.
200. So 226.
Yes. Yeah. Which is basically your width of a brick veneer wall.
Yeah. So that's an external.
Yeah. So durability, obviously, it's a softwood and it requires weather protection. Also requires termite protection. So for any building where the primary building elements are edible by termites, requires termite protection. And given that it's a flooring system, a water system, and roof system, you'll need to have some form of termite protection right from the bottom. So typically with things like timber trusses or so, if you've got termite protected timber to your frame, well then it doesn't matter about the trusses because they're not going to get to that point. But with the product, with a thing like CLT, because it's flooring, walling, and roofing, you need to have a continuous termite barrier to the building. So we'll have a look now at some of the other resources on here. So there's there's an article. This was from Wood Solutions about CLT, and have a look at that in your own time. But it covers some of the aspects that you may have to write about in your research report. So.
I'm still struggling to find a thermal, because thermal resistance of timber is actually very, very good. But concrete is very well defined. A lot of things are very well defined. Timber is actually not so well defined.
Mm-hmm.
And it's also the thermal mass. I'm struggling to find anything about thermal mass. I know they've been using like 70 mm thick walls in Europe for many, many years, as you know, and you're talking about freezing state places, you know. But the thing is, information about thermal mass is very, very negative.
Yes, yeah, timber doesn't have a very good thermal mass to it.
546 sort of like, it's related to two things, which is A, weight, and B, material. A, the density, and B, the nature of the materials, right? Because some materials don't have, you can get steel as dense as you like, it's got still a good thermal mass, and it's very heavy. But the thing is that sort of like, I think it's actually probably got more thermal mass than people give it credit for. It just has a higher resistance, so it doesn't take it up as quickly.
Look, I don't know. Like, the thermal mass of timber differs between your species of timber. So something like Pinus radiata has fairly low thermal mass, whereas something like Jarrah or Indian rosewood or your high density timber have a very high thermal mass because because they remain dense and they don't lose much of their weight through seasoning. Right. So whereas timber that does lose a lot of its moisture and weight during seasoning will have a lot more air in it, so has higher resistance to the passage of temperature, of heat and cool, but lower retention of heat and cool. But you mentioned steel, and steel is very conductive. Steel will conduct heat very well, hence but it still does have quite a high thermal mass. There is a lot of density to that material.
Right.
So we typically don't use steel in large enough volumes to contribute significantly to thermal mass, but if we were to have a cubic metre here of steel in the room, heat that up, that would retain
a lot.
That would take in a lot of that heat. We can put a lot of kilojoules into that cubic metre of steel, as opposed to a cubic metre of Pinus radiata. We would not be able to put many kilojoules of energy into that to then be released later on. Because steel is highly conductive, it will give off that heat much quicker than, let's say, a cubic metre of rammed earth or a cubic metre of concrete. It will,
or a cubic metre. I mean, it would take up a huge amount would have a high thermal mass, but if you had something like the same cubic metre of timber, it would take it in a lot slower. It would release it a lot slower, and there wouldn't be as much.
Yes.
But it would actually be a more effective heating system because the steel would. I think that's why we go for concrete. Is because it's got that mixture. It's got very low, but nothing like steel. It does give it off over time.
And that's why we're sort of getting into that thing about thermal mass not being the only consideration in terms of thermal flywheel, so the conductivity and stuff.
The resistance.
So I'll stop that recording so we can separate CLT. Actually, no, that's right. We're going to have a look at some more resources on here. So I've got two different websites up here. So this is, and they've got very similar names. I think it's unfortunate. So we've got Crossland and Xland, but but possibly you'd read the XLAM as CrossLam. So CrossLam, located in Western Australia, their website is really good in terms of details, both in PDF form and CAD details. So there's a whole series of details in there for you to have a look at.
Have a look at that span table.
Span table, that was right at the top, was it? I have this one, yeah.
Just very quickly.
Yes, for sure. So their span table is not written in the same way that, say, your floor truss span tables are written. What they've got is they've got dead loads and live loads here, and you can, and I don't fully understand it. I haven't contacted them to get that full understanding of what that dead load. So you've got your explanation down here, but yeah, we've got what appears to be dead load of a single panel, dead load of 2 panels, and then live loads as a function of But and then what you have is your deflections expressed as ratios. So it's not just saying this thing will span from here to here. You're allowed to do this from here to here. It will say if you use this thing to span from here to here, given this load, then it will have this amount of deflection. So it's a bit choose your own adventure as to how much deflection you will allow in your.
You're happy with.
How much you're happy with. So this is not constructed in the same way as many of the span tables you would have dealt with before, but I guess it's a little bit more particular, and it gives you that whole picture of loads, dead loads, live loads, and deflection as a percentage of your span.
And at some stage, they will probably, like over time, it will become very normalised what people think are okay in terms of deflective spans.
Well,
but not now.
The thing is, that's typically how engineers design commercial buildings. Things are actually deflecting all the time.
Yeah.
But the human eye doesn't like to see obvious deflection. So there are tolerances around deflection that engineers will accept. So they'll say we can have this many millimeters over this distance and people won't notice it. And that's the way things are designed. Because let's say one of those steel beams outside there, we could put a really heavy weight on it and get it to deflect 5 millimeters. Now, we don't want to do that for obvious visual considerations, or if we've got glazing underneath, we definitely don't want that to happen as well. But let's say there's no glazing underneath, we could probably put 10 times that load again on top of that steel beam, even though it's deflecting 5 millimeters, and make it deflect even more without it failing. It's not so much about this is we design close to failure. With commercial properties, it's about how much deflection will we accept, and everything deflects. Even this concrete slab that we're on right now will deflect ever so slightly under loads, under dead loads and live loads. So that's the way things are expressed in here. But it does give you an idea of what your capabilities are. So you've got 6 metre spans coming out of 2 layers, or 3 layers, or a 7 ply panel that's 220 millimeters thick. So compare that with your engineered timber joists, like high span joist, you around 400 mil deep for a 6 metre span. So half your depth.
You take that.
For that similar span, and 6 metres. That's about as good a span as you're going to get out of eagle flooring, out of any of the engineered joists as well.
That's enough.
So that's span table on the CrossLam page. Obviously, different manufacturers have different information. You can't go, okay, well, this is my information from CrossLab, I apply that as a benchmark for XLab, etc.
I mean, there's also something else, which is that they are at this stage. They are aware that there's going to be deflection. They are aware that there's going to be a perception around deflection, so they're giving you the deflection in their span tables.
Yeah.
So it's like if it deflects, well, you made that choice, as opposed to
as opposed to you just designing, okay, I can stay at this distance with this thing.
Yeah, exactly.
Yeah,
you made a choice.
But also, that's very important information for if you're glazing elements underneath these things. So we say, okay, well, within that span table, it tells us what our live loads can be and what the resultant deflection is going to be from those live loads, and then you can look at your occupancy or what the intended use is and say, well, this is our maximum expected live load. We need 20 millimetres of clearance before any window framing to allow that full deflection before we start cracking windows. So it enables you to design those final details for working out exactly what those tolerances need to be for your window framing, because yes, you do need to allow for some movement, but you don't want big, heavy, bulky details whereby the windows are packed out.
Yeah.
Decent depth underneath your.
Yeah. 1 in 200
Your
is 5 in a metre. So you 1 in 200 centimetres, 5. So it's about 50 mil. 1 in 200.
Over the 6 metres?
No, 50. If it's 1 in 200, 1 in 200 mil.
Yeah, I'm not yet.
5 metre. Yeah. 10 and over 6 by, so it's 30 mil over a 6 metre span if it's 1 in 200.
Sounds like a lot of deflection.
That's huge deflection.
Yeah. But I think the thing you'd want to do is get an explanation of those span tables. So I haven't done that. Haven't designed with CLT. Anyhow, plenty of details in PDF form, but also DWG files as well. So you can grab all those drawing files. Let's pick one at random. That's concrete. Let's do. Yeah, let's do concrete wall to ceiling. Let's have a look at that. So here we have concrete wall with a timber ring beam around that, and then our CLT fixed into that, and masonry fixing into the top of our, or a concrete anchor into the top of our concrete wall through that timber ring beam. So stacks of details there for you to have a look at, to download, to incorporate into your research assignments. Okay, so that's the CrossLab site, and here in South Australia, sort of between Victoria and West Australia. So whichever. Okay, let's not let me go back. So XLab site, really good for detailed description of the technology.
Right.
So a very, very good resource for that.
Australia, New Zealand has got blue laminated timber parts 1 and 2.
Yes. So what it says in here, I'll read it out. So as yet there are no Australian or New Zealand standards specific to the manufacture and use of CLT. However, CLT is very similar to blue laminated timber in that it's manufactured from finger jointed dried timber using glue lamination under pressure. So XLab manufacturer complies with the adopted standards which govern the design, preparation, finger jointing, planing, lamination and verification of XLab CLT products. So there are those Australian and New Zealand standards for glue laminated and finger jointed and timber structures, but not one that relates to building with CLT as you would have like AS1684 for timber that says if you do this and it will do this.
Might be worth trying to come up with a British standard actually.
Yeah, but I think I think for your design and implementation, it's probably better to go directly to the manufacturer's resources.
Absolutely.
It's the sort of thing that obviously you're not going to make your own cross-laminated timber at home.
How can we make cross-laminated timber?
And so you're going to have to get it from a manufacturer.
Yeah.
You might as well get that manufacturer involved in that design process, so you are confident about the certification and the warranty and the engineering, and that your private certifier can also be confident about the certification and warranty.
No, that's fine.
Yeah. So within this website, plenty of excellent information on cross-laminated timber, which maybe even stronger than may, help you very much with your research. I still don't have that full panel specification or the XLab design guide. So there's for all of those details, etc. There's on the CrossLab site. There's heaps of information in regards to that. Order this one if you wish. I ordered it a while back and it hasn't come. So but give it a crack. So navigate your way around that site. Won't bore you with those details anymore, and have a look at some of the videos to get an appreciation of the product and how
That's a video,
the technology, how it can be used, how it appears in buildings. There is actually maybe I'll drop a link to it later on rather than bore you with it this evening. There is another video shot in Australia about a cross-laminated timber building that was built and then tested for was it airflow changes, and rated very highly. So
it's really, it's quite dense.
Oh, the video.
No, not the video. Yeah. Sorry, I read I found there's some research that's heavily involved in testing it, and that was what I was searching desperately for.
So it was a passive house?
No, it wasn't a passive house. It was some guy called Mark. Something to do with timber. I think it was on Timber Tas. The Instagram Timber Tas.
Mm-hmm.
He's obviously down in Tasmania doing research. He's probably a university researcher, doing stuff on timber. It's industry research on massive timber values, and he was actually trying to work out as well what the thermal mass was, because it was better. It was actually better than what it was. Reported as, and definitely there was a big difference in thermal mass between hardwoods and softwoods.
Yes, yeah.
It was actually better than. I think the problem with a lot of things like this, particularly new things, and particularly things like timber, is that there's a lot of folk knowledge, but there's not a lot of technical knowledge, because it's never been commercially technical. Nowadays, research comes with money from the industry.
And this is a very new thing in Australia. Well, it's not new, but it's new in numerical terms of the number of buildings. So we've got one in Adelaide that I know of, and a couple in Melbourne. There are not many buildings using this currently, but it is the sort of technology that I think once it gains that critical mass, it has a lot of legs. So I think it's a good one to.
I'm just wondering
to keep
about
an eye on.
like just domestic design. You just house in a block. Potential to just use this house in a block stuff.
Yeah.
Once you've got a design, once you've got an engineered design, then just keep reproducing the same damn thing.
And very, very low impact buildings that seal
very well
and have no sound transmission. So So I think there'll be plenty of resources in those links for you. I'll grab that video after tonight's session and drop it into here as well, if I can find that, just as another interesting video.